Okay, I guess we'll get going. Everybody at home, can you hear me? Audio coming through okay? All right. So, we're going to continue on today with our discussion of HOMO versus LUMO. Our reason for this is because the first and great commandment of organic chemistry is nucleophile attacks electrophile. That's the theme of basically everything you'll encounter in terms of reactions in both 351 and 352. So that's the first and great commandment, and the second is like unto it. HOMO attacks LUMO. And if you've got that down and you can understand it, much of what we talk about will just seem like variations on that overall theme. So, let's just summarize the kinds of things we can expect to see in our quest for identifying HOMO versus LUMO in organic molecules. We have sort of as our lowest energy, most stable kinds of bonding orbitals. We have sigma bonds, including carbon-carbon, carbon-oxygen, carbon-nitrogen, carbon-fluorine, carbon-hydrogen. And these are almost never the HOMO. So in general, we'll ignore those sigma bonds in terms of thinking about reactive high-energy electrons. We do have sort of a group of less stable sigma bonding orbitals. These include carbon bromide, carbon iodide, carbon chloride. I guess I should make that, darn it. And also, let's see, carbon attached to maybe an oxygen where the oxygen is positively charged. But again, these are low enough in energy that they are almost never the HOMO of an organic molecule. Carbon-carbon pi bonds we tend to see here, also carbon-oxygen or carbon-nitrogen pi bonds. That might be the HOMO, although if it's a carbon-oxygen bond or a carbon-nitrogen bond, that tells you pi bond, that tells you that if there's a heteroatom there, an oxygen or a nitrogen, then likely you also have lone pairs on oxygen or nitrogen or some halide, all right? All of these are filled types of orbitals, but if you're looking to identify the HOMO, you're going to sort of look here for the highest occupied molecular orbital. I will point out that this section of orbitals, including the pi bonds and below, that's sort of the bonding region of our energy diagram. These are all orbitals that are lower in energy than our break-even point or lower in energy than the starting atomic orbitals from which they came. Lone pairs are examples of atomic orbitals. And another example of an atomic orbital that we've encountered is an empty 2p orbital. And that, if present, is almost always going to be our LUMO. If not, then we start to look for pi stars, carbon-oxygen, carbon-nitrogen, carbon-carbon pi stars. If not there, we tend to look for sigma stars for these weak carbon chloride, carbon bromide, carbon iodide, or perhaps carbon with a positively charged oxygen. People are always troubled. Just a second, this mask is bugging me. Have I got it on right? Okay, sorry. People are always troubled as to will they have to decide whether a LUMO is this kind of sigma star versus this kind of pi star? Generally not. In most of the organic molecules that you will encounter in this class, they'll be electrophilic at one spot, and you won't have to choose between, is it the carbon chloride sigma star or a carbon oxygen pi star? In fact, if you found both of those things in the same molecule, you might start to suspect that the molecule could be reactive at multiple positions. But I don't anticipate that you will find a situation where you're trying to decide, is it this one or that one? Sigma star of these or pi star of these. So look for one or the other. Probably aren't going to have to deal with both. And then up at sort of the highest energy level, you have the sigma stars associated with our strong sigma bonds. And those are almost never the LUMO. So you're going to look for highest occupied molecular orbital in the areas in blue, and you're going to look for the LUMO in the area sort of highlighted in red. And then I will point out that this area of our energy diagram, these are all antibonding orbitals. And if you fill an antibonding orbital, of course, you're going to break the associated bond. All right? That's sort of our summary. Right now, it's not clear to you why these sigma bonds are especially weak. Don't worry about that for now. For now, you can memorize it. We'll make that clear in Chapter 2. Okay? So with that in mind, we've shown you a couple of examples of HOMO of a nucleophile attacking LUMO of an electrophile. And I just want to briefly review them. But I guess before we do that, let's pause for any questions you might have. Yeah?
On the study guide, it keeps talking about draw the orbitals like superimposed. Could we do a couple of other examples of those?
Sure. The question was, the study guide often asks you to draw an orbital superimposed on a structure. I need a better word than superimposed. I think that's maybe a scary word. All I mean is to draw the orbital on the structure where it is. So for example, BF3, we've talked about boron-type compounds before. This is a molecule that is sp2 hybridized, trigonal planar, which means that you've got an unhybridized p orbital on boron. I'm drawing the opposite signs of the wave function on either side of that unhybridized p orbital, and that is the LUMO. I will tell you that BF3 is our electrophile. You will get better at recognizing electrophiles. For right now, I will tell you what an electrophile. I'll tell you that something's an electrophile, and then you need to think, okay, I need to pay attention to the LUMO. Similarly, we could think about this molecule, which looks like a strange sort of bat. It is actually diethyl ether. Used to be used as an anesthetic. This we'll call our nucleophile, and if it's our nucleophile, we care about what the HOMO is, and the HOMO of that nucleophile is likely the lone pairs on the oxygen. So to answer your question, this is what I mean when I say draw an orbital superimposed on the molecule. I just want to know that you know where that orbital is on that molecule. Because the location of the LUMO is going to determine the outcome of the reaction. HOMO attacks LUMO. That means, from an orbital energy diagram point of view, we would take the empty 2p orbital on BF3, and we're going to mix it with the lone pair on oxygen in our diethyl ether molecule. That's an abbreviation for diethyl ether. You shouldn't worry about it. We're going to mix those two orbitals together. Both of them were non-bonding to begin with, just two starting atomic orbitals. So we mix those together end on end. You can think of lone pair electrons on oxygen as being in something like a hybrid type orbital. You don't have to think about it that way, but it's perfectly fine if you do. We would have this lobe of the lone pair attack the matching lobe on BF3, end-on-end overlap, and that's going to give us a new sigma bond between oxygen and boron. The electrons from the non-bonding orbital will go there, and then we'll also make a new sigma star. Okay? So, if you predict the outcome of this reaction based on what we've discussed, you should have a new sigma bond between boron and oxygen. Your oxygen is bonded to three things and has one lone pair, so should have a positive formal charge. Your boron is now surrounded by four things, so it needs to be sp3 hybridized tetrahedral with a negative charge on boron, and that is the product of this reaction. Without knowing anything about the product, if you could identify HOMO and LUMO, you could get pretty close. In fact, you could probably draw the structure of the product directly. And this is the situation where you have a non-bonding lone pair and you attack an empty 2p orbital, which is also a non-bonding atomic orbital, you're going to make a new sigma bond, and that's it. That's the only thing you got to worry about. And as a result, there's just one arrow we have to draw the mechanism of this reaction. We draw the arrows starting with the electrons, the lone pair electrons, and we point the arrow towards boron at the place where the empty p orbital is. Okay? HOMO attacks LUMO. Questions? Yeah?
So I assume we're going to keep doing this over and over in chemistry, and we're going to start combining like really big chemicals that will, like when they combine, they'll form like chiral molecules. So like there could be two different forms. Will we just have to draw that twice?
Yes. So one interesting question is, in more complicated molecules, it's possible to get multiple products. You use the word chiral, which we haven't defined yet, but there are molecules that can exist with the same connectivity but two different shapes. They're called stereoisomers. And yes, in some cases, there will be the possibility of multiple stereoisomers forming. An example here that would not lead to stereoisomers would be, does the ether attack the BF3 from above or from below? Turns out here it doesn't matter because BF3 is symmetric. It exists, it's trigonal planar, and the top face is the same as the bottom face, so it doesn't matter whether you attack from above or below, you get the same thing. However, there will be cases where it does matter, and we'll deal with that, but not really until Chapter 5, where we learn about something called stereochemistry. Others, anything from the chat that I need to pay attention to? Not yet? Okay. Another example of this kind of thing, non-bonding lone pair attacking an empty p orbital, is the second step in a reaction that we will call SN1 later on. Don't worry about knowing that it's called SN1. This involves a carbocation, a positively charged carbon surrounded by only three things and therefore trigonal planar, positive formal charge on that central carbon. This is your electrophile. I'll just tell you that that's the case. If you didn't know that it was the case, a clue would be the fact that the carbon is positively charged. Another clue would be the fact that the LUMO is an empty p orbital, which is about as low as you can go for empty orbitals. And in this case, our nucleophile would be bromide, Br minus. And the HOMO of that atom actually is just one of the lone pairs on the bromine. You can think of it as in a hybridized orbital or perhaps a p orbital. It doesn't matter, but you're going to have end-on-end overlap of one of the lone pairs on bromine with the empty p orbital on carbon. You will draw an arrow from the lone pair to the empty p orbital pointing towards the carbon. Again, this is end-on-end overlap, so you're going to get a new sigma bond. It just so happens that in this case, after you form the bond, carbon is attached to four things, so it needs to be sp3 hybridized tetrahedral. And after the reaction, there's no negative formal charge on bromine and no positive formal charge on carbon. We get this neutral molecule as a result. Okay? So HOMO attacks LUMO. If they're both non-bonding orbitals, you just make a new bond and that's it. Only one arrow is needed. Okay? Questions? Yeah?
The colors that you're drawing, the purple and the orange, are those, what do those represent?
The colors purple and orange represent the mathematical sign of the wave function. In a p orbital, it switches from one side versus the other. What color I use where is arbitrary.
So those could be flipped and it wouldn't matter.
Right. The only thing is, technically, if you're going to make a new bond, the sigma bond comes from in-phase overlap of the same sign. Yeah. Okay. Yes?
So if the signs were flipped, like say that you colored the top on the
Uh-huh.
carbon and you colored it yellow, and like you could attack the bromine could attack the top.
That's right. If the question is, if I had arbitrarily decided to make this lobe in the p orbital yellow instead of purple, would the bromine have attacked on the top? I suppose so. My choice of wave function sign was totally arbitrary, and it's fine for you to realize that the top face and the bottom face of this carbocation are identical, and we can attack from above or below. Yeah.
And could that p orbital on the bromine have been on any of the lone pairs, or is it?
Could the p orbital that on the that lone pair or atomic orbital on bromine, could that have been any of the others? Yes. Bromine has 4 lone pairs. I guess technically 3, 4. One of them's a 4s orbital, so probably not that one. But then the other filled orbitals are the 4p, x, y, and z, and it could be any of those. Yep. Okay. All right, so now let's do a little bit more of a complicated situation. Let's stick with the lone pair because that's easy, but this is sort of situation number 2 where the HOMO is the lone pair and it attacks an antibonding orbital. So say a LUMO that is a sigma star. All right, and we'll make this situation similar to one I think that showed up in your study guide before. If not, that's okay. This is actually an example that is called the SN2 reaction, and we won't get to that till chapter 7. And it's not important at this stage that you know that it's SN2. I will tell you that hydroxide with a negative charge on the oxygen is your nucleophile, and this molecule methyl bromide is our electrophile. So we care about the HOMO on the nucleophile and the LUMO on the electrophile. Of course, the HOMO on the nucleophile is lone pairs on oxygen. And then how about our electrophile? What should the LUMO be? Got 4 sigma stars in this molecule. 3 of them are carbon hydrogen, 1 of them is carbon bromide. So, what do you think? Go ahead. Yep, LUMO's got to be the carbon bromide sigma star. You know it's that way because I told you that the carbon-bromine bond was weak, and that means that the sigma star is low in energy. We will learn soon why carbon-bromine bonds are weak, but for now, accept it as a given. Yeah?
How did you decide whether
good. How would I know which is the electrophile and which is the nucleophile? Both of them have lone pairs. You will be able to do that at the end of chapter 2. We will talk about why hydroxide with a negative charge on it is more reactive than Br minus with a negative charge on it. In this case, though, the Br is neutral, and so you would be inclined to think, okay, the one with the negative charge is probably more reactive. But I wouldn't have asked you to decide that at this stage. I would tell you, one is the nucleophile, one's the electrophile, and then you've got to assign HOMO versus LUMO. So the HOMO I'm not going to draw. It's just one of the lone pairs on the oxygen. You could think of those lone pairs as just being in one of oxygen's atomic orbitals. It's fine if you want to think of that oxygen as being sp3 hybridized, and each of the lone pairs is in an sp3 orbital. I won't argue with that. The LUMO, we're going to draw a node in between the carbon and the bromine. We're going to have small lobes facing the node. They are small because they have destructively interfered with each other and canceled out. I'm using color here to represent the opposite wave function sign. I could just as easily have chosen that one be purple and the other be orange in a different way. I must shade in the large lobes that point away from the space between the two nuclei, that point away from the bond. I have to shade them such that this lobe in back of carbon is opposite in sign to the one that's in front of carbon, and this lobe in back of bromine I have to shade opposite in sign to the one that's in front of the bromine. That's what the sigma star looks like. Now, HOMO attacks LUMO. You've got a bit of a choice to make. Lone pair attacks, are we going to attack the carbon or are we going to attack the bromine? At this stage, you may not know, but you can think about it a little bit and make a prediction. If the oxygen attacked the sigma star at carbon, you're going to make a new bond between oxygen and carbon, and it's going to involve end-on-end overlap. So it's going to be a sigma bond because one of the lobes of the atomic orbital on oxygen is going to attack the corresponding lobe of the sigma star on carbon. So I would form a new bond with carbon, but since it's a sigma star, what's got to happen to the sigma bond? You fill a sigma star, you do what to the associated sigma bond? Yes, you break it. Now, where are the electrons going to go? Are they going to stay on with carbon? Probably not. And why is that? Okay, this is a math question, and the way you get to it is, can you count? So what would happen if those electrons stayed on that carbon? I would have too many electrons, 10 electrons around carbon, and we don't do that because of the octet rule. That would require population of an antibonding orbital, actually. So we break the bond and the electrons go onto bromine, and bromine leaves. So the product of this reaction is, here's my new sigma bond, and here is bromine that just left. All right. Now, these are the products that we observe. Just some of you may be troubled, though, thinking, well, why couldn't the oxygen attack the bromine? All right, let's think about what would happen if that were the case. I'm not going to draw those options because it doesn't happen, but some of you may be interested in why that's the case. First, if the oxygen attacked the sigma star at bromine, we would make a new oxygen-bromine sigma bond. That's very weak. That's a very weak bond. In fact, the oxygen-bromine bond would be reactive like bleach is reactive, only even more. So if you've ever dumped bleach on your hand after you dumped it on your shirt, and your shirt suddenly loses its color and your hand starts to feel a little funny. If you have that's the bond between oxygen and chlorine in bleach. That's what makes bleach work. It would be way worse to have bromine for reasons we'll discuss later. So you'd make a weak bond. Second, the electrons would have had to leave with the carbon, and having negative charge on a carbon localized and not stabilized by resonance is very unstable for reasons that we'll discuss in chapter 2. So for now, the other option just doesn't lead to very stable products. This option leads to the most stable products. All right. Yes?
Isn't it also because the bromide ion is more electronegative, so it pulls some of the electron density towards it and away from the carbon ion?
Sure, you can think of it that way. There is an electronegativity difference between carbon and bromine. It's not huge, but it's enough that you would predict that there would be a small partial positive on the carbon. And so, yeah, you can rationalize the outcome that way as well. Good. What else? Okay, so the point is you put electrons in a sigma star, you're going to break the associated sigma bond. Let's keep going with lone pairs attacking LUMOs. So our third example will be lone pair attacks of a nucleophile. Some highest occupied molecular orbital of a nucleophile attacks a pi star. Okay. So let's do, say, this molecule, which is it's called ethoxide. It is the conjugate base of ethanol. This is going to be our nucleophile, and again, the HOMO is going to be lone pair on oxygen. Let's have our electrophile be this aldehyde. Okay? Based on what we've talked about, though you haven't seen this aldehyde before, what do you think its LUMO is? Got to be the pi star, the carbon-oxygen pi star, right? Okay. It might help us to draw that, to remember that this aldehyde is trigonal planar about that central carbon. That is, the carbon is sp2 hybridized, and both the methyl group and the proton and the oxygen all have to be in the same plane, which I'm trying to represent with this sort of gray parallelogram. We're sort of looking side on onto the plane. If I were to draw that pi star, there would be a node in between the carbon and the oxygen, and then there would be a lobe on above and below the plane on carbon. And if you actually did the calculations, you would see that the lobes on this side are angled away from the bond between carbon and oxygen. And then we would see a similar thing on oxygen, where the lobes would be oriented away from the space between the two bonds. A lot of times I would have just drawn this pi star as just looking schematically like two p orbitals adjacent to each other but out of phase. I'm going to use either of those drawings interchangeably for the pi star. Now, an interesting point that I've made here that's consistent with the calculations is that most of the LUMO, maybe as much as 70% of the LUMO, is actually on the carbon and not on the oxygen. I don't expect you to know that, and there's a way you could reason through it, but it won't be important to us really until 352. So for now, you can accept that as a matter of fact, just something that comes out of the calculations. If I tell you most of the LUMO is on carbon, then where should my nucleophile attack? Probably on carbon. HOMO attacks LUMO, draw electrons from the HOMO, which is one of these non-bonding orbitals on oxygen. And I'm going to have it attack carbon, attack the LUMO, the pi star, on carbon, because that's where most of the LUMO is. Now, if you didn't know that that's where most of the LUMO is, one thing from resonance and Lewis structures can help you out. There is a resonance structure you can make by taking the electrons in the pi bond and moving them out onto oxygen. Oxygen would still have a full octet, but with a negative charge. The carbon would only be surrounded by 6 electrons and have a positive charge. Now, you may look at that and say, that resonance structure is a minor contributor because you have unnecessary charge separation and carbon doesn't have an octet. Okay, fine, but would you agree with me that the alternative resonance structure in which electronegative oxygen is positively charged and the lone pairs are on the carbon, would you agree with me that this is way worse? Simply by electronegativity alone, right? So what resonance tells you is that, you know, you may be sort of meh about this resonance structure, but you'd be really sort of Mr. Angry Eyes about this one, right? What this tells you is that the aldehyde is electron poor on the carbon and electron rich on the oxygen. So that's another reason why you would attack at the carbon, because that's the most electron poor spot. Now, we're not done yet because we've just filled an antibonding orbital. So which bond am I going to break? The pi bond associated with that pi star. The electrons are going to, because we made a new bond with carbon, the only place those electrons can go is onto the oxygen. And our product here, I'm going to highlight in red our new sigma bond between the oxygen of our nucleophile and the carbon of our electrophile. That carbon is now bonded to 4 things, so it has to be tetrahedral, sp3 hybridized, and the oxygen's got to have a negative charge on it. Okay? So that's filling a pi star, breaks the pi bond. Questions you want to ask so far? Yeah?
Are antibonding p orbitals ever hybridized?
Are antibonding, sorry, what?
P orbitals, are they ever hybridized or will they always?
Are antibonding pi orbitals ever hybridized? I guess, do you mean by that, will we ever see, say, a pi bond that comes from 2 sp2 orbitals lined up? No, generally not. There is a reason for that. Because pi bonds hold electrons farther away from the nucleus, and because sp2 orbitals have s character, the sp2 orbitals are actually more electronegative than the p orbitals, and they would prefer to be involved in sigma bonds where the electrons are held closer to the nucleus. Yeah. So you could imagine it happening, but in general, no. It'll be more stable for the electrons in the hybrid orbitals to be involved in sigma bonds. Okay, what else? Anything on the chat? No? Okay. And then I think the other example we want to deal with is, what about using a pi bond as a nucleophile? And I think I've talked with some of you about this in office hours, and it's also in the study guide. So here is an alkene, And this is going to be our nucleophile. And then here is our electrophile, HBr. So for the alkene, we care about the HOMO. Hopefully you can see that's the carbon-carbon pi bond. For the electrophile, we care about the LUMO, which can only be the sigma star between hydrogen and bromine. So again, I'm going to try to draw this pi bond as though we're looking, that's terrible, sorry, as though we're looking down along the edge of the plane that contains the pi bond. And schematically, I guess, I'm going to show a lobe of electron density above the plane and a lobe below the plane. Understand when I do that, that most of the time when I'm drawing a pi orbital, I will instead draw it with sort of like it were two p orbitals on adjacent carbons but in phase. But those two things mean exactly the same thing. And then, let's see, I will use gray shading to indicate, and I use gray shading enough, we'll put it on the favorites there, to indicate that the orange lobe is below the plane of the molecule and the purple lobe is above. Okay? With me so far? That's the HOMO. The electrons in that pi bond are the HOMO. The LUMO is the hydrogen bromide sigma star. If we're going to make that, we would put a node in between the two nuclei. On this side, we'd have a small lobe and then a larger lobe on the back side. This sigma bond between hydrogen and bromine comes from perhaps a p orbital on bromine with a 1s orbital on hydrogen. And here we're going to do the out of phase combination to give us the antibonding orbital. And so that's going to sort of look like this, with a node in between the hydrogen and the bromine. Okay, so HOMO attacks LUMO. I'm going to draw an arrow from my pi bond, or from the pi orbital, the electrons in the pi orbital, to the sigma star. Now at this stage I have to ask, which of the two am I going to attack, the hydrogen or the bromine? And it turns out HBr is an acid. It's a Bronsted acid. It's a good proton donor. And also, you could think of electronegativity as one reason why we'd attack the hydrogen instead of the bromine. There's partial plus on the hydrogen and partial negative on the bromine. Another explanation is if you do the math, a lot of the LUMO is on the hydrogen. In any case, that's where, so accepting that I tell you that we're going to attack on the hydrogen, if you attack there, you break the hydrogen-bromine bond. So your products should be Br minus, because we broke the bond. Now it gets a little tricky. What are we going to have on the other side? What do you suppose happens when the pi electrons attack that hydrogen? Go ahead.
Does the hydrogen bond with one of the carbons, another carbon has a positive charge?
Yeah, so the answer is, that was given is, does the hydrogen bond with one of my two carbons and then the other one gets a positive charge? Okay, good. I mean, you have to pick one way or the other, right, if we're going to make a new bond. Any other options that you see? Okay, if not, that's fine. Somebody asked about another option in office hours, and it turns out there is one, though it's one that we wouldn't really even worry about unless you take my graduate level chemistry 552 class, so I guess I will not talk about it. I will restrain myself even though it's kind of cool. Yeah, we're going to form a bond with one of those two carbons. So that's the hydrogen, and I suppose, yeah, this is the new bond that we made. And the other one is going to, I'm sorry, I don't know what's going on there. Whoops. I'm getting a little confused. Join the club, you say. Okay, one of the two carbons gets the hydrogen, the other has a positive charge on it. Now, how do you know which one of those two carbons gets the hydrogen? In this case, if you look at the molecule, I deliberately chose the molecule so they'd be identical, so it doesn't matter. Yeah, go ahead.
There's just a lot of people in the chat wondering how you know that one's the nucleophile and the other one's the electrophile.
Okay, great. So folks at home are asking, how do you know that the alkene's the nucleophile and HBr is the electrophile? You wouldn't necessarily know that yet. You will learn by experience that if you have a carbon-carbon pi bond, generally the pi star for the carbon-carbon bond is high enough up that it's not going to be that great of an electrophile. With experience, you will also look at HBr and recognize it as a strong acid. Bronsted acids also tend to be Lewis acids, which also tend to be electrophiles. We're going to get there, but it's okay if that isn't really clear at this stage. For right now, if I told you one was the nucleophile, I'd expect you to identify the HOMO. If I told you one was the electrophile, I'd expect you to identify the LUMO. Yeah?
Just because you mentioned it, what was the other option?
Okay, fine. What is the other option? Well, you could imagine maybe an intermediate where instead of the hydrogen making a full bond with one of the carbons, oops, I didn't want to erase that. Instead, it sort of hovers over both of them, and you have the pair of electrons that used to be in your pi bond shared evenly between the hydrogen and the two carbons, and the positive charge shared all between them too. It's almost as like the proton just sits down in the cloud of pi electrons and hangs out there. That concept is called a 3-center 2-electron bond, and it's hard to draw a Lewis structure for it, and some people hate it. So we will pretend that that option doesn't exist and just work with that. All right. Any follow-up questions on that from the chat?
I don't think so.
Okay. All right. All right, so we've seen a lot of highest occupied molecular orbitals attack lowest unoccupied molecular orbitals, and that basically finishes us up with chapter 1. Now we need to build the intuition to recognize good nucleophiles, to recognize molecules that have high energy reactive electrons versus molecules that aren't very reactive as nucleophiles. And it turns out that the tools for doing that are hidden already within things you learned in general chemistry. So what makes a good nucleophile good? All right. Turns out the answer to this is hidden in the world of acid-base chemistry, Bronsted acid-base chemistry. It turns out that asking what makes a good nucleophile good is the same thing as asking what makes a weak acid weak. What makes a bad nucleophile bad is the same thing as asking what makes a strong acid strong. Okay. So let's take a moment to think about acid-base chemistry. And we'll do so by considering some generic, no. we'll do so by considering something like HCl and water in equilibrium with each other to give Cl minus and H3O plus. Hopefully, I don't need to remind you that when we think about acids dissociating in water, that it's not just that the HCl bond breaks, the proton pops off, and you have H plus and Cl minus, because that doesn't happen in water, ever, worlds without end, okay? Instead, what happens is HCl donates its proton to water to make hydronium, H3O plus, and then Cl minus. So you can ask where the position of this equilibrium lies, and we'll think of some tools to figure this out. But we want to introduce a few terms that should be familiar to you from Gen Chem and which I won't talk about that much. On the left side of our equation is an acid, and the thing that's left over when it loses its proton is called a conjugate base. On the left side of the equation, water is our base, because it's what gets the proton. And over here, the H3O plus is our conjugate acid. You could also think of it in the reverse way and call H3O the acid and H2O its conjugate base. You should be very good at that. You should be very good at identifying conjugate bases of acids. It should sort of roll off the tip of your tongue or come to the top of your head or whatever metaphor you want. But you need to be able to do it in your sleep, backwards with your eyes closed while hopping up and down and humming the alphabet backwards or something like that, okay? It needs to come that easy. So let's suppose I tell you, and it's actually true, that the equilibrium in this particular case favors the right-hand side. That tells you a couple of things. It tells you HCl is a stronger acid than H3O plus on the other side of the equation. It also tells you that H2O is a less stable, more reactive, or stronger base than Cl minus. Okay? Acid-base equilibrium tells you the relative stabilities of the acid and base on one side and the conjugate acid and conjugate base on the other side. So just by virtue of the fact that I told you the right-hand side of the equilibrium dominates here, you know that HCl is a stronger acid than H3O plus, and water is a stronger base than Cl minus. Now, what does that tell you about their nucleophilicity? H2O, HOMO is lone pairs on oxygen. Cl minus, HOMO is lone pairs on chlorine. Which is more nucleophilic is the same thing as asking which is the stronger, less stable base. Based on this information, which do you pick? H2O. Every time, right? This is the less stable base. It is more reactive. It is the more reactive nucleophile. And you can conclude, therefore, that the electrons are higher in energy and that's a better nucleophile. Okay, so that's all we have time for today. You should be finished up with study guide, the demo study guide by tomorrow. And you really ought to be doing the study guide 2. Try to do a third to half of it before we meet again on Friday.